Howdy, today on Flippin Science we're talking about chromatography. Howdy, today on Flippin Science we're looking at chromatography. So science understandings we're going to look at thin layer chromatography, gas chromatography, high performance liquid chromatography and ion chromatography. They all involve the use of a stationary phase and a mobile phase to separate out mixtures. The rate of movement is caused by differences between the strength and retraction between the mobile and stationary phases. That's caused by differences in polarity and charge. And you need to determine from data the composition of elements of the mixture. So chromatography is a technique used to separate out mixtures and identify the components of mixtures. It separates out components based on their chemical structure, their polarity and their charge. It's useful for solving crimes, and it's also very important to figuring out the chemicals involved inside plants in photosynthesis. So it has very important and relevant uses in chemistry. So there's many different types of chromatography. So we've got paper, which is also thin layer chromatography, column chromatography, HPLC, so high performance liquid chromatography, gas chromatography, and ion chromatography. I'm going to go into detail in ion chromatography in a separate video, so keep a lookout for that. So in paper or thin layer chromatography, you dot your mixtures on the bottom of a piece of paper. You dip that into a solvent. You can use water, you can use ethanol, you can use any solvent you like. And due to capillary action, the components move up the paper, but the rate at which they move up the paper depends on the structure of the material inside your mixture. Column chromatography is a little bit different. You have a thin glass column, and into that you place a substance that is your stationary phase that separates out your mixture. So in here we would have silica gel. You add your substance at the top, the substance separate out through the column, and then you can elute the different substances as they come out and collect them separately. And then you could go on and do some more identification from there. HPLC, high performance liquid chromatography, it's a very similar idea to column chromatography, but you use a pump to push through the substance, so it happens a bit faster. But you also get better resolution than you do from column chromatography because the output is a bit more digital when you get graphs, for example. You can get an idea about how much sample is coming out as well as the difference in the samples as they come through. Gas chromatography is very similar. The sample is injected into a column and is carried by a gas this time instead of a liquid solvent. The gas travels along the column, and then as the substance passes out of the column, you get a digital readout. Ion chromatography is a little bit different. You have beads of a resin that have either a positive or a negative charge on the outside. Your mixture has positively or negatively charged substances in there, and depending on their charge they stick to the beads. And then they come out, and you can force them out using a solvent with a particular charged salt in it, for example. We're going to go into this, like I said, in another video, so look out for that. So in each of these chromatography techniques you have two components, a mobile and a stationary phase. The mobile phase is comprised of a solvent or a carrier gas or a carrier fluid that carries the sample through and past the stationary phase. So the sample and the solvent, they flow through, and you get a separation based on how much sticking you get between your mobile phase and the stationary phase. Here are some examples of the mobile phases that are used. So in paper or thin layer chromatography, it is the solvent that you're placing your paper or other substance into. In column chromatography, it's the solvent that's carrying your substance. In high performance liquid chromatography or ion chromatography, again it's the solvent that's carrying your sample. And in gas chromatography, it's an inert carrier gas, so it's usually something like nitrogen. The stationary phase is the material for which the components that are separated on separate out on. And they do that due to differences in polarity or charge, and we'll go through that in a second. The stationary phase's job is to slow down your mixture as it passes by, and the amount of slowing down is determined by the chemical structure of the substances that are passing through. So, example of stationary phases in paper chromatography or thin layer chromatography, it's paper usually. In column chromatography, it's the solid inside the column, and like I said before, it's usually silica. In high performance liquid chromatography, it's the column, the substance on the inside of the column, I should say, and in gas chromatography it's the same. Here's an example of a column from a gas chromatograph. So the sample is injected in one side and it passes through the column, and it's on the edges of the column that you have your stationary phase. In ion chromatography, it's the ion exchange resin, the beads that are present. So how does chromatography work? We're going to focus mainly on polarity in this video, and we'll talk about charge more when we're talking about ion exchange chromatography. It's based on polarity. So polar molecules, they have a distribution of charge that means that one end of the molecule is negatively charged and the other end of the molecule is positively charged. And it's usually a partial positive or negative. So if we look at water, for example, the oxygen is strongly electronegative, so it has a partial negative charge. It's pulling the electrons from the covalent bond with the hydrogens towards it. And hydrogen atoms, they have a partial positive charge because the electrons are closer to the oxygen than they are, and that gives them a slight positive charge. So this is polar. Non-polar molecules have an even distribution of charge across the molecule. The rule is that if your stationary phase is polar, you're going to attract polar substances, and if your stationary phase is non-polar, you're going to attract non-polar substances. We'll briefly talk about charged substances and ion exchange chromatography. So a charged substance will stick to a substance of the opposite charge to itself. So in ion exchange chromatography, you have beads that might have a negative charge, for example. So any substance passing by that has a positive charge will stick to those beads, and it will take them longer to get through the column, and in fact they might even not go through the column because they get stuck to so many beads. Whereas a substance that has the same charge as the surface of the beads will pass straight through because it's repelled. So here we have a negatively charged substance. The beads have a surface with a negative charge, so it just passes through because they repel each other. So let's talk about how paper or thin layer chromatography works. Let's use an example using ink. So coloured inks are made up of different coloured inks that are mixed together, and those substances might be more polar or less polar than others in your mix. The stationary phase, if it's paper is very polar. The cellulose present has lots of hydroxyl groups, so it's a very polar substance. So that means the polar parts of your mixture of dye will stick to the paper really readily. The non-polar or less polar substances, they won't stick to the paper as much, so they'll be carried along with the mobile phase. So let's look at some examples. So if we look at our yellow ink here, it is sticking to the paper more. It is not rising as quickly with the solvent, the water in this case, as the blue ink is above. So this yellow ink is more polar than the blue ink is here. The blue ink is less polar. It's not sticking to the polar stationary phase, so it's being carried along with the mobile phase and raising higher. So the principles of paper or thin layer chromatography apply to gas chromatography as well. The column, here's our column. So if the column, for example, has a non-polar stationary phase on the inside, non-polar substances are going to form dispersion forces with that, and they will stick to the non-polar stationary phase. So it will take them longer to come out of the column. So here we have a straight column, but like we saw before, they make big loops of these. So if we have a non-polar stationary phase, non-polar substances are going to be attracted to that, and it will take them longer to be injected in and then pass through and then come out. And that's what we show on your digital readout. You see a different retention time. So you might want to identify the substances from your chromatograph. And you can do that in a few ways. In paper or thin layer chromatography, you can use an RF value. So an RF value is where you calculate the difference in movement of the substance versus the solvent. And that should be fairly consistent for a particular substance as long as you do the experiment in the same way every time. So let's have a look at an example. So the way that you calculate an RF value is you divide the distance that your substance moves by the distance that the solvent moves. So let's have a look at an example down here. So we'll calculate the RF value of this pink dye down here. So we're using the average point of the average space, I guess, that the dot takes up. We're measuring that. We're also measuring how far the solvent goes to figure out what our RF value is going to be. So the dye moved 32 millimeters, so we're going to get my calculator up. So we're going to do 32, and we're going to divide that by the difference that the distance that the solvent moved, which is 66. So 32 divided by 66, we get 0.48. So our RF value is 0.48 for the pink dye. Reading graphical data using retention time, so high performance liquid chromatography and gas chromatography, you'll get a feed out like this. You have a measure of time down the x-axis, and then you have arbitrary units on the y-axis. This all depends on the polarity of the column that you use. So if you have a polar column, a polar substance will spend more time in the column and thereful will have a longer retention time. It will take longer to come out the other end. So let's assume that our stationary phase is polar. Over here, our isohamilton, that has a really long retention time of 31.6 minutes. So this would be very polar as long as the stationary phase is polar as well. Whereas our Rutan down here, it has a low retention time, so that means it went through the column really, really quickly. And because of that, it didn't absorb onto the surface of the stationary phase very much, so it wasn't attracted to it. So if our stationary phase is polar, then this would be a non-polar substance or a less polar substance. So let's look at some example questions. So here we have a crime scene chromatograph, a person 1 and person 2. So explain how the chromatograms above indicate that person 2 is more likely than person 1 to have been at the crime scene. What we're doing is we're going to compare the peaks. So if we look at crime scene and person 2, we have this peak in common, we have this peak in common. We're missing a peak here, we have this peak in common, this peak and this peak. So there's more peaks in common with crime scene 1 and person 2 than there are with person 1 and the crime scene. Another question says, long chain carbon compounds D, E and F were all found in a sample of soil from a crime scene. Structural formula is shown below. Chromatograms were obtained using a polar stationary phase. State whether peak X on the chromatogram is most likely to be due to compound D, E or F. So if we look at the graph here, we can see our time is 0 here. As we go along, it's important here that they told us it's a polar stationary phase. So what that means is that if the substance has a long retention time, that means it's absorbed very strongly to the polar stationary phase. And that tells us that the substance itself is polar. So if we look at our 3 compounds here, we're going to look for the most polar compound because that's giving us our last peak here. So the last peak here, very polar because it's absorbed most strongly to the polar stationary phase. If we look at these, not particularly polar, some polarity, very polar. So we got the carboxylic acid group at the end there. So that tells us that since this molecule here, compound F, is very highly polar, it's most likely to be peak X. As it's polar, it would absorb most strongly to the polar stationary phase, and that would give it a long retention time. So on Flipping Science today, we looked at chromatography, we looked at how it works, we looked at mobile and polar stationary phases and RF values. That's it for Flipping Science today. See ya!